So in our last lesson we ran into an issue where we had unbalanced equations, and that's what we're going to do today. Is we're going to learn how to balance these chemical equations, and what that means is to have the same number of atoms of a particular element on either side of the reaction arrow. So if we look back at our problems from before, here's an example of an unbalanced chemical equation, and we can see that it's unbalanced because, for instance, on the left side of the reaction arrow, or on the reactant side, we have 3 chlorines, and on the right side, or the product side, we have 2. And that's a problem. So there's the law of conservation of mass and matter that says that we can't just lose particles. We can't destroy them. So our equation needs to reflect that. We do not do that by changing the chemical formulas themselves, instead by adding coefficients in front of those formulas to balance the reaction overall. So it's very simple. There's only 2 steps. The first thing you need to do, and this is what you learned the other day, is to write the skeleton equation with the correct formulas. And I'm being really intentional about this because you have to write the correct formulas first. If your formulas are incorrect, your balanced equation will not be correct. Once you have done that, then we look at the overall reaction and we use coefficients to balance the overall equation. And then up here, there's a little mnemonic that could help. It's exactly what it sounds like or looks like. It's MINOH, not spelled correctly, obviously. And that is a suggested order in which you could tackle the different elements when you're balancing them. So this suggests that you balance the metals first, and then the ions, specifically the polyatomic ions, then the nonmetals, and then any free oxygen or free hydrogen that you have. And by that I mean diatomic oxygen and hydrogen, not oxygen and hydrogen inside of other compounds. This is just a suggestion. It doesn't work perfectly every time, but it's a good way to get started. So for our first example, we have water decomposing to form gaseous oxygen and hydrogen. So we've got H2O. All right, and for our purposes, we're just going to assume that it's liquid. Decomposes to form. So notice this is one of those instances where we only have one reactant, and that's okay. This is called a decomposition reaction. We'll cover that more later. To form gaseous oxygen and hydrogen. So notice I'm leaving a space here. That's where I'm going to put my coefficients. So gaseous oxygen, remember, is diatomic, as is the hydrogen. Okay, so that's the correct skeleton equation. You'll notice our issue comes because we have 1 oxygen on the reactant side and 2 on the product side. So we know we didn't just magically get rid of an oxygen. We have to account for that somewhere. Our hydrogens are already balanced. Notice that we have 2 hydrogens on the left, 2 hydrogens on the right. That might get thrown out of whack as we proceed to balance. That's okay. We'll take care of all of them. So what I'm going to do is put these lines in front of each of my formulas, and that's where I will put my coefficients. Okay. Now, notice up here it says have the same number of atoms of an element. Okay, that doesn't say of all elements. That just, what that means is if I have 2 hydrogens on the left, I need to have 2 hydrogens on the right. That does not mean I need to have 2 hydrogens and 2 oxygens and etc. Okay, so all elements don't have to be the same as each other. Just one element has to be the same on one side of the arrow as on the other side. Okay, so if I look at MINOH up here, there are no metals that I have to deal with, so I can skip that. There's no polyatomic ions. Yes, I have nonmetals, but specifically they are oxygen and hydrogen. Okay, so if I look at my oxygen first, again, on the left I only have 1. On the right I have 2. So what I'm going to do is put a 2 as a coefficient in front of my water molecule here. So what that means effectively is I need 2 water molecules to make this reaction happen. 2 separate water molecules. Okay, so if I have 2 H2Os, what that effectively means is I now have 2 oxygen atoms, but I also have 4 hydrogens. Okay, so I've got 4 hydrogens on the left, still only have 2 on the right, and the way that I can fix that is by adding another coefficient. Okay, so now I have 2 hydrogen molecules. Each hydrogen molecule has 2 atoms in it. That's what this little subscript means. And 2 times 2 is, of course, 4. Okay, so then I go back and double check. 4 hydrogens on the left, 4 hydrogens on the right. 2 oxygens on the left, 2 oxygens on the right. I do not need a coefficient here to make this work. If you want, you can put a 1. You don't have to. It's just like in algebra where x is the same thing as 1x. Okay, so that one's pretty easy. Next we have phosphoric acid and sodium metal react to form sodium phosphate in solution and hydrogen gas. So phosphoric acid is of course H3PO4. Acids are always aqueous. Sodium metal, so it's just going to be Na, and if it's in its metallic state, that means it's solid. Reacts to form sodium phosphate, which is Na3PO4 in solution, so aqueous, and hydrogen gas. And again, remember diatomics. Okay, that hydrogen should be diatomic. All right. Notice I wasn't paying attention to the overall balancing as I wrote out the formulas. Okay, I didn't let the fact that I have 3 hydrogens on the left change this formula. I wasn't paying attention to that at all. I have to write the formulas correctly first. Now I can go back and balance the whole thing. And once again, I can use MINOH as a suggestion. This is one instance in which it won't work perfectly for me, but that's okay. It still works as a framework. So this suggests that I start with the metals, and generally that's a good idea. Sodium is a metal. On the left side, I only have 1 sodium atom. On the right, I have 3. Okay, to fix that, I'm going to put 3 as a coefficient right here. Okay. Next, it suggests that I tackle the ions. What that means is if I'm looking for polyatomic ions, and I do have a polyatomic ion, I've got phosphate. This simplifies things if you can look at the ion as a whole, because then I'm not trying to count individual phosphoruses and individual oxygens. I can treat this as one thing. And so far my phosphates are already balanced. There's only 1 phosphate in this formula, there's only 1 phosphate there, so I can go on to the next thing, which is nonmetals. I don't have any others besides hydrogen, and that's the last thing on our list. This is where we run into a slight problem. On the left we have 3 hydrogens, and on the right I have 2. Okay, so I can't just put a coefficient in front of one of these, I have to put a coefficient in front of both. And the best thing to do is to look for a number that both of those numbers go into. So 3 and 2 both go into 6. So I need 6 hydrogens on the left and 6 hydrogens on the right. To make 6 hydrogens on the left, I'm going to put a 2 right here. So now I've got 2 whole phosphoric acid compounds, which gives me 6 individual hydrogen atoms. And then over here, I'll put a 3. Okay, so once again, I've got 3 hydrogen atoms. What you may have realized already is that this messes up my phosphate balancing. I now have 2 phosphates, okay, 2 PO4s. I can fix that over here. I'm just going to put a 2. Okay, and that does mess up my sodiums. I now have 6 sodium atoms, and I can fix that by just turning this into a 6. This is going to be a guess and check process. It's supposed to be a guess and check process. Don't be upset if you have to go back and change a couple of numbers. That's supposed to happen. Do notice that these 4 numbers cannot be reduced. Okay. If I had written 4, 12, 4, 6, that would be incorrect. I would have to reduce them to the lowest numbers together. Okay, I did not say that correctly mathematically. I'm not going to let that bother me right now. All right, moving on. We've got 2 more examples. Okay, these are both combustion reactions. And actually, looking back, my goal for these first 2 problems was for you to pay attention to diatomics. Make sure you're not missing that. And then this was an example with polyatomic ions. Okay. All right, next we have tricarbon octahydride gas. So it's going to be C3H8 gas. Burns in the presence of oxygen, that just means reacts with. This is a combustion reaction. You'll learn more about it later. I'm using the wrong color. You know how that bothers me. Fixing it, moving on. Oxygen gas. To form gaseous carbon dioxide and water. Now that I have my equation written, I can go back and add coefficients to balance it. The reason I wanted to do this problem is because on the right hand side and the product side, you can see that I actually have oxygen in 2 different places. Okay, so I'm going to make a note of that here. Oxygen in 2 places. And yeah, you got to count both of those, so you have to make sure you don't miss any. There are no metals or ions in this equation. We can dive straight into our non-metals, so I'm going to start with my carbon. Over here in the tricarbon octahydride, this is also called propane, by the way, I have 3 carbons. I only have 1 in my carbon dioxide, so I'm going to put a 3, meaning I am going to produce 3 carbon dioxide molecules. Okay, I'll tackle the hydrogens next, because they're in this compound. Anytime you have elements all by themselves, save them for last. Here I've got 8 hydrogens, and over here I have 2. So to make that work, I'm going to say that I'm going to produce 4 water molecules. Okay, and I'm saving oxygen for last. That's now. So notice over here, I've got 6 oxygens from the carbon dioxide, and I've got a further 4 from the water. Okay, so I've got 10 total. That means I need 10 on the left side as well. Sorry if you heard my kiddo crying there. So I need 10 oxygens on the left-hand side. Oxygen is already diatomic, so I need 5 of those oxygen molecules. Okay. Last one. This is going to look really similar. So we've got gaseous hexane. We've got C6H14. Okay. It's another combustion reaction, burns with oxygen, produces gaseous water and carbon dioxide. Okay, and I'm going to go back and balance the whole reaction. Okay, so I've got 6 carbons on the left, so I'm going to make it so I produce 6 carbon dioxide molecules, so I have an equal number of carbons on either side. On the left I've got 14 hydrogens. That means I'm going to need 7 H2Os to balance that out, which leaves me with my oxygen. So again, just 2 starting on the left. On the right I have 12 coming from the carbon dioxide, okay, and then 7 coming from the water, okay, and 12 plus 7 is 19. Over here, I'm starting with O2. There's no whole number that I can multiply 2 against to get to 19. Alright, so I'm kind of stuck. What that means is I'm going to have to scale up the whole reaction. When you encounter this situation, the thing that I'm going to tell you to say to yourself is to double the fuel. Alright, so this is a combustion reaction, which means we're burning something to produce energy and other byproducts. Here's your fuel right here. When you run into this, I have an odd number on one side, an even number on another side with a diatomic. Go back and double your fuel. Okay, so now I have twice as much carbon and twice as much hydrogen. So before I only needed 6 carbon dioxides, now I need 12. So I'm going to cross that out. I'm going to put a 12 down here. Again, this is guess and check. It's fine. I only needed 14 hydrogens before. Now I need 28. Okay. So now I have a grand total. Sorry guys, Skylar's nap time is ending sooner than I thought. So I'm going to hurry through this. So now I have 12. No, okay. I've got 24 oxygens from the carbon dioxide and 14 from the water. That's 38 total. 38 divided by 2 is 19. So now that reaction is fully balanced. Again, sorry for the crying baby.